Welcome on this video about groups and fields. This chapter is going to be split in two videos. The first one is going to speak specifically about groups and fields, and the second one will be about inequations, which can be really tricky sometimes. Groups are sets with one operation plus many properties. Fields are set with two operations and many properties. Which properties? A cool way to remember the properties of group is to remember Aanik, A-A-N-E-K. A cool way to remember Aanik is a song. Aanik uni shawani na 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 na. This is a song that we sing to children in France. It's actually a Native American song. If you don't know it, the link is in the description. What does these letters stand for? A stands for abgeschlossen. In English, it would be closure. A associative, N for natural element, E for inverse element, and K or C for commutativity. So we have four properties to be a group, and if on top of that there is another property, it's a special group, the commutative group, that we also call Abelian groups. Let's go through them. For all A, B of M, A star B should be of M. Closure, the Abgeschlossenheit, means that when you apply the operation to two elements, the result remains in M. Associativity is when you change the position of the parentheses. For example, if you take three elements, A, B, and C of the set, when you do that, it's the same thing as that. The only thing that changed is the position of the parentheses. 3 and 4 are more interesting. The neutral element is an element of the set, so that for all A of the set, when you apply the operation between A and the natural element, you keep A. So it doesn't change A. The inverse element is an element which depends of A. Here we have an element for all A. Here it depends of A. So we call it A minus 1. This is just a notation. It helps to think of it as 1 divided by A. So for all A of the set, there is such an element that when you do the operation between A and the inverse, you keep the neutral element. We found it in the third property. Let's take examples for this. So let's take the set R, the real set, and the plus. So which thing, when we add it to A, let A stay A, 0. Now, what is the inverse of A? So that when I add it to A, I obtain 0, the natural element for the plus. A minus 1 is equal to minus A. For the multiplication, what should I do to A so that it remains A? Yes, I should multiply it by 1. And now what should I do to A to obtain 1? Yes, I should multiply it by 1 divided by A, which is a part of R. Of course, 1 divided by 0 would not be okay, so that's why we remove this 0. Let's recap. What element when you add it doesn't change anything? 0. What element when you multiply it doesn't change anything? 1. What element when you add it you obtain 0, the neutral element for plus? Minus A. What element when you multiply it you obtain the natural element for multiply? 1 divided by A. Because A times 1 divided by A is equal 1, which is the natural element for multiply by. Now, commutativity. It's just that A operation B is the same thing as B operation A, and when you have it, the group is called a commutative group, or also called Abelian groups. Typical Abelian or commutative groups are the integer with the plus, the rational with the plus, the reals with the plus, the complex with the plus, the rational without 0 with the times, the complex without 0 with the times. But not this. Why? We are going to see it in the practice. Let's go to fields. A cool way to remember fields is to remember duck. In German, we can use K for commutativity. For a field, we need a set and two operations, the plus and the times. It should satisfy three properties. M and the plus should be a commutative group. M without 0 and the times should be a commutative group. And the distributivity that we saw in logic, the first video, A times B plus C, the same as A times B plus A times C. Typical fields include the rationals, the reals field, and the complex field. This is not a field. Let's practice. First, I want you to prove that this is an abelian group, and then I want you to prove that this is not a field. It's a ring, but you don't have to remember that. Let's correct it. So the integers plus is an abelian group because its abgeschlossen, associativity, natural element, inverse element, and commutativity are true. Abgeschlossen, I just wrote the definition. I don't know how to prove it more. It's really axiomatic, kind of. For the associativity, I have this, and this comes from the associativity for plus, so I cannot write more either. For the natural element, careful to write that this 0 is from set. It's the natural element of the set, because for all a in the set, and when you add it, it doesn't change anything. The a plus 0 is equal to O, plus a is equal to a. The inverse element, it's the inverse element for plus, which is minus a. This is the way I write it. And for the commutativity, it comes from the commutativity from plus, so we cannot write more than that for now. And to be a field, this should satisfy 3 properties, which is that the set with plus should be a commutative group. This is true, we should just show it. The set without 0 and time should be a commutative group. And distributive law should satisfy it. But actually, this is not true, that the thing is a commutative group, because there are many elements without inverse. Because, for example, so counterexample, 2 belongs to the integers, but there is not such thing as inverse for 2 for the multiplication in the integers, because the inverse that would, when you multiply it, get the natural element for time, that is 1, is 1/2, and this is from the rationals, not the integers, so this element, it doesn't exist. You want to read more about groups and fields? You can look to the link in the description. I linked an Oxford PDF. It's really well written and it's really short, so if you want to read a bit more, it's really cool. Do you have any ideas or suggestions? Please share them. See you in the next video.